This video is on the design methods of a buck boost converter operating in the continuous current mode. In particular, we will look at the design equations for the output filter inductor and the filter capacitor to meet a given high frequency ripple specifications, and we will also look at the selection criteria for the MOSFETs and the diodes of a buck boost converter. In a previous video on the buck boost converter analysis, we have analyzed the operating principles of the buck boost converter shown here in detail, and we also derived the input-output relationship to be VO over Vn equals D over 1 minus D, with D between 0 to 0.5 resulting in the buck mode of operation, and D higher than 0.5 up to 1 resulting in the boost mode of operation. And we also saw that the buck boost converter produces a negative output voltage with respect to the input ground. Using this input-output relationship, we can also establish the D under any given operating condition to be VO over VO plus Bn, which comes directly from this equation. Now, for constant output voltage and variable input voltage applications that we are interested in, we can determine the range of variation in the operating D for a given range of variation in the input voltage. So the D varies from a minimum of VO over VO plus Vn max to a maximum of VO over VO plus Vn minimum. So higher the input voltage, smaller is the D, as we would expect. So the first step in the design process is to establish this range of variation in the duty ratio, because we will need that to determine the worst case conditions for various parameters. Now, in the previous video on the buck boost converter analysis, we looked at the various current and voltage waveforms at different points in the circuit. We analyzed that in detail, and those are shown here. And among these, we'll be using the inductor voltage and current waveform and the capacitor current waveform to come up with design methods or design equations for the L and C components. The voltage and current waveforms for the buck boost inductor are shown here. So the voltage is Vin during the on interval, and the inductor is connected to the output, so the voltage is minus VO during the off interval or the 1 minus dTs period. The inductor current has the slopes given by the voltage divided by L, and its average value we have analyzed is the sum of the input and the output load current. In plus IO is IL average, and this peak-to-peak variation is what we define as delta IL. Similar to the buck as well as the boost converter design, in the buck boost also the suggested design method is to select the L to limit this delta IL or the peak-to-peak variation in the inductor current to some specified value. Now, this delta IL value can be obtained arbitrarily because the inductor is an internal the inductor current is an internal variable, so we are really free to choose an arbitrary value for this delta IL. So we may choose this to be following the previous design methods of buck and the boost. We may choose this to be about 10 to 20% of its own average current, which for a buck boost is In plus IO. In some other applications, we may be given a minimum load value, and we may be interested in maintaining this continuous current mode all the way down to that specified minimum value. Under that condition, the delta IL choice would be decided based on meeting the CCM requirement. In any case, regardless of how we choose the delta IL value, once we have made that choice, then the expression for the inductance L required to meet the chosen delta IL under any given operating condition can be derived as shown here. So essentially, the equation for L di over dt is VL. Therefore, considering, for example, the off interval, di is delta IL, the duration dt is 1 minus dTs, the off interval, and the voltage across the inductor during the off interval, its magnitude is VO. So from this expression we get the required value of L for a given delta IL to be this expression, VO times 1 minus dTs over delta IL. So again, the VO, TS and delta IL, once we have selected the value, they are all constants, and only the 1 minus d term is it varies with the variation in the input voltage. So the question is, what value of d within the given operating range should we substitute in this expression? And since we try to design for the worst case condition, the worst case would be the value of d that maximizes this equation, and therefore it is really the minimum d minimum is what gives the maximum value for this expression. That ensures that delta IL would be less than or equal to the chosen value regardless of any value of d. Also, similar to the boost converter case, and unlike the buck converter, in a buck boost, the choice of the inductance L does not significantly affect the capacitor selection. In a buck, higher the value of L, smaller is the capacitor for a given output voltage ripple specifications. But in both the boost as well as the buck boost, there is no such strong correlation between the L and C in meeting the output voltage ripple specifications, and the two can be designed independent of each other. This slide lists all the parameters required for the selection or the design of the buck boost inductor. From the previous slide, we saw that the required inductance of the L is given by this expression, and here we should substitute D minimum to for the worst case design considerations. The other parameters include the peak value of the inductor current, and that is the sum of the average current plus 1/2 of this peak-to-peak ripple. The average current is IN plus IO, which can be written completely in terms of the load current IO as IO over 1 minus D. So that is IN plus IO, and that is written here. And for the maximum value of this IL peak, we should use maximum load current and also the D max value plus 1/2 of this delta IL. The other required parameters includes the DC bias, which is simply the average value of the inductor current. Again, it's IO plus IN, and in terms of the load current, it is IO over 1 minus D, and we should use IO max and D max in this expression. Finally, the RMS value of the inductor current is an important design parameter, and that is given by this expression. Essentially, this is obtained by taking the mean square of the DC component, which is just the DC component square, plus the mean square component of the high frequency ripple, the triangular waveform. The sum of the two gives the total mean square of this waveform, and take the square root, we get the IL RMS. And in many cases, the delta IL in comparison to the average value can be very small, so this can be neglected. Under that condition, the IL RMS is approximately equal to simply the IO plus IN, or in terms of the load current, it's just simply IO over 1 minus D. Again, we should take the maximum value for IO as well as D. Next, we look at the selection of the output capacitor. Very similar to the boost converter case, in the buck boost also, the capacitor selection is decided mostly by the RMS current requirement for the output capacitor. The reason is the RMS current, it can be even larger than the maximum load current value itself. Here is the waveform of the capacitor current. During the switch on interval, the capacitor supports the full load current, so the capacitor current is negative IO during the on interval, and during the off interval, the current is the inductor current minus the load current, so it's essentially IL minus IO is the capacitor current during the off interval, and its average value only during the off interval is, since IL average is IN plus IO, so this is equal to IN plus IO minus IO, so it's essentially IN. So we can approximate this capacitor current waveform by the square wave current shown by the dotted lines, taking on values minus IO and plus IN. Now if we try to derive the RMS value of this current, that is neglecting the high frequency ripple component, then the IC RMS is the simple expression. So essentially we take the square IO squared times the duration as a ratio of the total period, so that is D, plus in the next interval it is IN squared and the duration of 1 minus D. So that gives us the mean square ripple. Take the square root to get the RMS value. Now in this expression, if we substitute IN equal to IO over D over 1 minus D, which is obtained from the power balance, if we substitute that here, then we get the final required value of IC RMS to be IO times square root of D over 1 minus D. So that is an identical expression to that of what we derived in the boost converter case. So once again, for D higher than 0.5, the RMS current can be even larger than the load current itself, and that is the reason why we say the capacitor selection is dominated by this RMS current requirement. Now if we consider the high frequency ripple also in deriving the RMS current value, this is the expression that we get, and this is again identical to the boost converter expression. So I will not go through the derivation again, but I will simply state that the delta I adds only a very small amount to the RMS value, and that is illustrated by the plots of RMS current as a function of D for 3 different values of the peak-to-peak ripple current. The red waveform, the red plot, which is barely visible, corresponds to the base case of 0 ripple, and the green is 20% ripple, and the blue is 50% ripple. So as can be clearly seen, even for as high a ripple as 50% of the average current, there is almost a negligible increase in the RMS capacitor current. So we can certainly use this approximation for the RMS current determination. We can also see from this plot that for D higher than 0.5, somewhere here, beyond this point, the RMS current value is larger than the load current itself. This slide summarizes all the parameters required for the capacitor selection. So essentially we will be selecting the C based on the RMS current requirement as discussed in the previous slide, and in the expression we should use the maximum load current value as well as the maximum D to obtain the worst case RMS current. Once we select the capacitor based on this requirement, it is mostly likely that it will also meet the delta VO specification, the output voltage ripple specification, which is an important performance specification. But it is we still need to verify if that is indeed the case by looking at the expression for delta VO, both due to just the ideal capacitive component as well as due to the ESR. Now considering just the ideal capacitive impedance, once again considering, for example, the on interval, so where CdV over dt equals IC, and that gives us the delta VO to be the IC, which is IO in this interval, times dt, which is the duty ratio times TS divided by C. So that is the delta VO specifications. So once we select the C based on the RMS current requirement, substitute that value of C here, and make sure that the resulting delta VO is significantly smaller than what is the maximum allowable delta VO from the specifications. The reason why we want it to be significantly smaller is because we are in the next point we are going to say that the delta VO, actual delta VO, is dominated mainly by the ESR component. So the delta VO due to the capacitive component should be negligibly small. So that brings us to the ESR limit. Similar to the other converters, mainly the buck and the boost converters, ESR is once again given by the maximum delta VO allowed divided by the maximum peak-to-peak variation in the capacitor current. For a buck boost, this peak-to-peak variation in the capacitor current is simply the inductor current, neglecting the ripple component of the inductor. Then delta ICO is again IO plus IN, the average value of the inductor current. So this expression gives the required ESR. This is the upper limit. So any value of any capacitor that has this RMS current rating and ESR less than what is obtained by this expression, that should be sufficient. And we should also ensure that the voltage rating is at least the output voltage plus some sufficient safety margin. Finally, we come to the selection of the switches, the MOSFET and the diode. We need the voltage, peak, RMS and average current ratings for the different devices. So for the MOSFET, if you look at the voltage rating, consider when the switch is off, then the diode is conducting. Therefore, this end is minus VO with respect to the ground. Therefore, the voltage across the switch is Vin minus of minus VO, that is Vin plus VO. So that is the required voltage rating, and that is one of the drawbacks of the buck boost topology. So the voltage rating is much higher than what is needed in the buck, which was Vn, or in the boost, which was VO. So it is the sum of the two that calls for higher voltage devices with corresponding disadvantages in terms of higher RDS on and so on. The peak current rating again is another drawback of the buck boost. The peak current rating is the sum of the input current and the load current plus this 1/2 of high frequency peak to peak ripple component. The RMS current rating, the switch conducts the inductor current, which again neglecting the high frequency component, it is IO plus IN, but it conducts only for the duration of DTS. So we need to multiply by square root of D to get the RMS current through the switch. And substituting IN equals IO times D over 1 minus D, we get the expression for the RMS in terms of the load current to be this value. Similarly, for the diode, the voltage rating again is Vn plus VO. We can get that by considering when the diode is off and the MOSFET is conducting. The peak current is still the same as the switch because they both carry the inductor current during the appropriate intervals, and therefore they have the same peak current rating. For the diode, it is the average current rather than the RMS current which is more relevant. So the average current through the diode, as can be clearly seen by average KCL at this point, it is simply the load current. So we need to consider the maximum load current to get the diode average current rating. Finally, I would also like to discuss a few points worth noting regarding the buck boost converter. The first thing is the buck boost. This particular topology of buck boost gives a negative output with respect to the input ground, and this may not be suitable for several applications. So for those applications where we still need both the step up and step down capability, then there are other buck boost topologies like the SEPIC, which can provide a positive output voltage. The second one is, if the applications require only step down, then use a buck. If it requires only step up, use a boost. So only if you need both step up and step down under different operating conditions of the same converter, then we have to use the buck boost. So if it is, for example, if it is only a step down applications, then the buck converter would be far more efficient than using the buck boost converter. Even though both of them can achieve step down, we would prefer the buck because of the advantages in terms of efficiency, the size of the filter, and the cost. Another main disadvantage, in addition to the switch ratings, is the fact that both the input side as well as the output side currents in a buck boost are pulsating. In a buck converter, the output current is a smooth inductor current, whereas the input is pulsating. In the boost, it's just the opposite. The input current is smooth, output is pulsating. Whereas in the buck boost, it combines the sort of the disadvantages of both the buck and the boost. Both the currents are pulsating. So for example, if there is a stringent requirement on the high frequency content in the input current, then we will need an input LC filter for the buck boost converter case. And the last point is the buck boost is very popular in its isolated version called the flyback converter. So this when we look at the isolated converters, we see that flyback converter results in probably the minimum number of components for the same specifications, and it's very easy to obtain several isolated outputs using this flyback topology.